In this video, we'll be looking at a recursive implementation of a moving RMS or moving root mean squared, both looking at the theory, a derivation, and how to implement that in software in C and on STM32 microcontrollers. For the live implementation, we'll be using this custom DSP board I designed specifically for audio applications and videos such as these. We have an STM3287 microcontroller, an audio codec which contains ADCs and DACs, various other peripherals, as well as a USB connection which provides data and power, and serial wire debug for programming and debugging. If you'd like to learn more about the actual design behind this hardware and what peripherals there might be on this and how to route and lay this out, make sure to check out video number 78 on my channel, which goes through exactly that. Thank you very much to PCBWay for sponsoring this video. I had these DSP audio boards manufactured and assembled by them, and they've turned out great. I'd highly encourage you to check out their services, and I'll leave a link to them in the description below. Thank you also very much to Altium for sponsoring this video. I used Altium Designer to design this audio PCB we'll be using for the real-time software implementation of the moving RMS detector. And if you'd like to give Altium Designer a try for yourself, check out all the cool new Altium 365 features. Make sure to check out the link in the description below, or go to altium.com/YT/PhilsLab to get yourself an Altium Designer free trial, as well as 25% off your first license purchase. To start off with, we'll look at RMS Basics, why we might need and use an RMS or root mean square. Then we'll move on to the recursive version and also looking at a moving RMS, which is a variation on the traditional RMS, so to speak. And lastly, we'll see how we can implement that derivation in code in C and have that running in real time on an STM32 based embedded system. The discussion of RMS comes up typically when you're trying to get an average or current average or mean of an AC signal. Typically, if looking at DC signals, it's very straightforward, of course, to get the average, but for AC signals, this can be a tiny bit more complicated, and we have various measures of doing so. If we, for example, try to average or take a mean of the magnitude of AC signals, a lot of the times, and especially for sinusoidal signals, on average we would end up getting a value of 0. If we think of the typical sine wave pictured on the left-hand side here, on continuous time, a sine wave varies between a positive and negative amplitude, and if we take the average across, for example, one of these cycles, the average would be 0, and that of course isn't very helpful as a measure of what amplitude this signal actually has. Similarly, on the right-hand side, we can see the same approach in discrete time, where we have a sampled signal, in this case also a sine wave as well. If we sum these samples, divide by the number of samples for a sine wave, typically we would get 0, because it's a symmetric signal. We would like to be able to deal with all cases of AC signals, including sinusoid, and get some sort of measure of an average of an amplitude or magnitude for that AC signal. Of course, we have other measures, for example, peak or peak to peak, but those measurements don't really tell us much about an average or some sort of trend, very simply speaking. The solution to this problem, oftentimes, is the root mean squared, or RMS for short, and very simply speaking, we can think of that as an AC average. We'll see this a lot also in AC power calculations and so on. It's very straightforward to compute. All we have to do is square the magnitude, and we have the equation for the continuous time RMS here. So we're squaring the magnitude, we're computing the mean by integrating and then dividing by the total signal time. Similar approach for discrete time as well, where we sum the samples and divide by number of samples, and then we take the square root of the result to essentially undo the squaring we did initially. As an illustration, let me show you this on a graphing calculator. I have this sine wave plotted, sine function to the sine of t, plotted from 0 to 2 pi, so a single cycle of a sine wave. Equation h1 of t essentially is a simple mean, so we're integrating from 0 to 2 pi, essentially taking the mean, dividing by 2 pi, so this is essentially taking the mean. If I enable this function, we can see that the mean is of course 0 because this is a symmetric function. Very simply speaking, we're computing the area under this sine wave, and of course that'll end up being 0. The RMS solves this by first of all squaring this sine wave, and I've plotted this in green. This is what happens when we square a sine wave. Essentially, squaring eliminates the negative portion of any signal, because negative times negative is of course positive. Then to compute the RMS, all we have to do is take this squared signal, integrate it, divide by the total time, and then take the square root. And we can see that on the left-hand side, this h2 of t is doing exactly that. If I enable this function, we get the root mean squared, and that's of course a constant value. This constant value is 0.707. This turns out to be 1 over the square root of 2, and is a common result for the RMS value of a sine wave. I can of course also add a constant in front of my sine wave, for example a times sine t, so squaring that would be a sine t squared, and then I can compute the RMS as well. If I, for example, double my amplitude, so that a equals 2, we can see our original sine wave in red, we can see the squared sine wave in green, and the RMS value is this black constant here, and that's gone to 1.414, meaning it's 2 times 1 over root 2. The RMS value of a sine wave is the peak amplitude of the sine wave divided by root 2, so a very simple result. And you can see how this is quite useful for getting some sort of average value of an AC signal. And this is exactly the result shown here. So for example, for a sine wave with peak amplitude A, the RMS value of that sine wave is the peak amplitude divided by square root of 2. And there's similar results for triangle waves, square waves, and so on. In general, being able to compute the RMS is very useful. Some example use cases might of course be for power calculations, but also, for example, in audio processing, we want to get a current mean level of this fluctuating AC audio signal. And this can be used, for example, in audio compressors, audio noise gates, and anywhere where you have to detect some sort of envelope. The question now becomes, how do we move from a continuous time domain into a discrete time domain, and how do we compute, for example, an RMS on a microcontroller or using C code in software? One alteration we're going to make is looking at a moving RMS. Essentially, we're not computing over the whole length of the signal. So for example, when we turn on our audio processing system to the time we have now, we don't want to be computing for all that time. What we can do instead is look at a moving RMS. And this only looks at a small subset of the total samples. This moving RMS is characterized by a length L. We'll call this a sliding window, so to speak. So we'll get an average of the previous L number of samples up to the sample now. In the digital domain, of course, we work on discrete samples, and then we have this formula here, which initially looks a bit complex, but actually it turns out to be very simple. And this is the equation for moving RMS in discrete time. The output is y of n, so we're computing RMS samples or values at every sample n, and our input is x. So we have input samples and output samples. What we do with the input sample, x of n is our current input sample, we square that, we add to that the previous input sample, we add to that the previous input sample squared, and so on for the whole window length. So if L is 10, we would do this for the current input sample and all previous 9 input samplers as well. So we add the squares together, as is common with an RMS, divide by the total number of samples, in this case we denote this by the capital L, and that whole sum and division we take the square root of. So very, very simple. We're adding squared input samples of a certain number, this could be 3, 5, 100, 1000, and we're taking the square root of that, and that is our current RMS value. So it's discrete time and it's moving. One question, of course, is how do we choose L, and we'll see that more in detail later on with some simulations. One problem we might have is that for large values of L, so if we're looking at a large window, a large horizon for our moving RMS, we need to do a lot of computations. Keep in mind we have to store and remember all of these previous input samples just to compute the current value of the RMS. So we need a lot of computations, we'll probably need quite a lot of large memory and so on, and it's not very efficient. In comes the savior, which is the recursive version of the discrete time moving RMS, and this is really quite elegant and very easy to derive. We start again from our previous equation where we're just summing squares of our input samples, dividing by the number of input samples, and then taking the square root. If we expand that equation, for example for yn, and then for yn minus 1, we can derive the recursive version. Let me square both sides, so I'll square yn squared, and that gets rid of the square root on the right-hand side. Then we can have an equation A, which is yn squared, is this sum, and we can have equation B, which is the previous RMS output, so yn minus 1 squared. If we expand these two equations, and sorry for a bit of a maths-heavy video, we can see some common occurrences. For example, xn minus 1 squared appears in both, xn minus 2 squared appears in both, assuming of course L is larger than 2, and the final terms xn minus L plus 1 squared appear in both. If we subtract B from A, a lot of these terms will cancel. So xn minus 1 squared will cancel, xn minus 2 squared will cancel, and so on. And then what we're left with is the current RMS value squared minus the previous RMS value squared is the current input sample squared minus the nth previous input sample squared divided by the number of samples. So that's quite a mouthful, sorry for that. It's easier to visualize with this equation, but it turns out we can do this recursively. Rearranging this, all we have to do to compute the RMS is store the previous output of the RMS, store the current input, which is x of n, and the nth previous input. So we don't have to compute all of these sums of previous inputs, and we can have a pretty large L, and we only need to store that previous output and the nth previous input. Now this is really, really straightforward and very, very fast to compute. To store, for example, xn minus L squared, we can just use a circular buffer. This is very easy, and I'll show you how to do that in just a second. Before we move over to the actual implementation in C, and I'll walk you through in detail, let me show you some MATLAB examples to see how, for example, the window length will change the response of our moving recursive RMS. I've written a simple recursive RMS function in MATLAB, which takes in an array, which might be our input array, a sinusoid, whatever signal we want. We take in the sample rate in hertz, and what, for example, RMS horizon in seconds we want. Because of the limited window length, for example, if you want to look at a 1 Hz signal and we're sampling at 48 kHz, we'll need to have a window length of 48,000, so L equals 48,000. However, if you're only looking at faster changing signals, for example at a kilohertz, then of course, at a sample rate of 48,000, you can have a much shorter window length. Essentially, we can compute our window length by multiplying the sample rate in hertz times the required RMS horizon in seconds. You can ignore this for now, we'll go into detail in the C implementation. For my input signal X, now I've simply taken a sinusoid with peak amplitude 1 and a frequency of 1 Hz, so a very slow moving signal. This will allow us to see how long the window needs to be of our moving RMS to be able to capture the RMS value. Remember, the RMS value of an amplitude 1 sine wave is 0.707. If I compute my recursive RMS, my sample rate is 1000 Hz, for example, and let's just say we only want a very short RMS horizon of 10 milliseconds. If I plot this now, again blue is my input signal and Y is the output of my recursive moving RMS. Because the window horizon, this RMS horizon in seconds, is so short compared to the actual input signal, we can see the recursive moving RMS has real difficulties estimating the RMS value. We can try again by increasing the RMS horizon, for example, to the 10th of what we have in our input signal. Plotting that again, it's still not very good. Let's try exactly 1 second as our RMS horizon. I've extended the input signal a tiny bit, so rather than going from 0 to 1, I'm going from 0 to 5 seconds, and we can see the output, essentially our moving recursive RMS in red, starts at 0 of course, and then as we continue, the moving RMS settles in about 1 second to about 0.707. So the recursive method of course takes some time to settle, depending on what signal you might be looking for, and so on. Let me increase the RMS horizon as well, maybe to 2 seconds, and let's see what the difference is here. Now we can see it actually takes 2 seconds for the recursive RMS to reach the actual RMS value of the input signal. So you always have to tailor your recursive RMS window length to whatever signals you're looking for. And this is especially important, for example, if you're doing noise gates. You could maybe do multiband noise gates. One part of the noise gate is looking for low frequency signals, where you need a longer RMS horizon, and you might have a noise gate which looks for high frequency signals, where you need a shorter horizon. This is quite interesting to play around with. Let's jump over to STM32 Cube IDE, where we'll be looking at how to implement this moving recursive RMS in real time in C and on an STM32 microcontroller on an audio processing platform, which we saw at the beginning of the video. This is very simple and very straightforward. I have my moving RMS header file and I have a moving RMS C file. Let's go through both and then let's see how we implement that in main.c. Because I want static allocation, I'm going to give myself a define here, a constant, essentially saying what the maximum window length is for my recursive moving average. This is fairly arbitrary. It depends on the frequencies of the signals you might be looking at. Then I typically have a struct. This will store, for example, the RMS output. It'll store the window length, my circular buffer, and so on. Also the window length L, of course, you want to store. And then I also have this constant here, which I compute initially. And this is 1 divided by the window length. And this is a constant we'll be using over and over again. So it does make sense to pre-compute that. Then we have our circular buffer. We have count, which is a variable which points to the position we're currently at in the circular buffer, and the circular buffer itself. Keep in mind, you might notice here these _sq or square variables, and this is because we are storing the square of the RMS at all times. If you remember back to the slides, the actual recursive equation you can do by not having to square root the whole time in the save sum operations. We can perform the square root operation when we actually want to use the RMS value, but for the recursive implementation, we can just stick with having the squared values, and that's why you see this square in the C files as well. Then we have the output squared as well. We have 2 functions. One is to initialize, which will 0, for example, the circular buffer, which will compute 1 over window length. And then we have our update function, which computes the actual RMS, or rather the square of it. And that takes simply the current input sample as a floating point variable. Moving over to the .c, or the source file, in our initialization function, we take the struct as a pointer, and then our window or RMS length L. we store the window length and 1 over the window length in our struct and set up circular buffer pointer to 0 and then clear the circular buffer and clear the output. Very, very simple initialization function. The interesting function, and where all the magic happens, so to speak, is in the update function. We take the struct as a pointer and we take the current input sample, so this is x of n, as a float. All we're doing now is implementing the square of this equation. So essentially we're implementing this form of this equation. X of n is our input sample, y of n is our output sample. What I'm doing first is I'm computing my input squared and I'm storing that in the current position of the circular buffer. Remember, we have to store all input samples in the circular buffer and we'll need to access them when the time comes, so when L samples have passed, and this is what we're saying in this equation here. So I'm storing the current value in the circular buffer because we'll need that in L computations. Then I'm updating the circular buffer pointer, so if my count has reached the length of my circular buffer, I reset the count or my pointer back to 0, otherwise increment that counter. So very, very simple circular buffer. After that, we implement the actual equation. Our current output sample squared is the previous output sample plus 1 over L times the input sample squared, the current input sample squared, minus the Lth previous input sample squared. Exactly what we have in this equation. Then we return the square of the RMS, and that's as straightforward as it is, and you can see very, very efficient to compute. I won't be going into very much detail of how to set up an audio processing platform, for example for the STM32 microcontroller. However, if you're interested in that, I have various videos on my channel, for example video number 55, which goes through exactly that. How to set up the I2S streams, input-output, how to perform double buffering with DMAs and so on. I'd strongly suggest you doing so if you're interested. Now looking at main.c, of course I need to include my moving RMS header file. Then, of course, I need to define my RMS struct, which I'll just call mRMS. I also have my RMS window length, which I can play around with. I'll just set this to 2048. My sampling rate for this system is currently at 48 kilohertz. Then I have this float variable, which is the mRMS square estimate. We still need to take the square root if we want to actually get the proper RMS, so to speak. In my processing function for my double buffering, all I'm doing is looping through the input sample and then computing the RMS using the moving RMS update function, passing in all my input samples. In int main, all I have to do to set up my moving RMS is pass the struct and as well as the window length. We'd of course like to see what the RMS value is, and to do that I'll just print the RMS value via USB to a console, maybe with PuTTY or HTML, and we'll see that in just a second. All I'm doing is I'm calling this code at a certain interval, for example at a 100 millisecond interval, 10 times per second. I'm computing the square root of our RMS estimator, which is the actual RMS, don't forget, and I'm feeding that on as a float to my USB output. And that's all there is to this code. It's very, very straightforward. I have this DSP processing board now hooked up with a serial wire debug connection to an ST-Link. I've also hooked up USB-C, which is providing data and power to this board. And this is hooked up to various potentiometers and audio jacks where I can feed input and output signals to. To do that, I'm using this Analog Discovery Pro by Digilent, and I've got my WaveGen connected to the input, and I'm just using one of the oscilloscope channels to monitor the input as well, which you might not need. We simply just need to do the WaveGen so we can supply an input waveform, for example triangle, square, or sine wave, and to measure the RMS we are getting from our estimator. Now let's give this a try. Looking at the Wikipedia root mean square page, if you're interested, of course, there's more detail on the RMS itself, but there's also a table of common waveforms. For example, the sine wave we already saw, the RMS value should be the peak amplitude divided by root 2. We also have the square wave, or we might have a triangle wave, which is the peak amplitude divided by root 3. So let's see if our system actually detects this and gives us the proper RMS values for a given input. Back in Cube IDE, I have my device connected via serial wire debug. I've got my USB cable plugged in for power as well. So I'll just click on the run icon and then upload it via SWD and my ST-Link to the board. There we go. Now the device is running. I have HTML open, which I can connect to a virtual COM port. My STM32 microcontroller appears as COM3. So I'll just click connect. And what we're getting out at the output is an estimate of the RMS. Currently I have no input signal going there and we're getting about 0. As we saw, I also have a Digilent waveforms connected where I can generate a waveform at the input and also monitor that waveform. If I open the waveform software side by side, my WaveGen is currently not enabled, but it's set to 1 kHz sine wave and an amplitude of 500 millivolts. If I click run, on the left-hand side, our RMS immediately jumps to 0.35. Remember, we're running at 500 millivolts, so therefore RMS value should be 0.35, pretty much bang on, so that's really great. Let's double the amplitude, so to 1 volt, and then we should get 1/√2. Let me change it to 1 volt, and we can see immediately we get 0.707 as our RMS estimate, so that's pretty cool. We can also try out different waveforms. For example, we could try a triangle wave at 1 volt, and that's 0.57 or 0.58. According to Wikipedia, it's the peak amplitude divided by √3. So 1/√3 is about 0.577, and that's exactly what we get here. So it looks like our moving recursive RMS is working very well. But keep in mind that we have a very short window length compared to the sampling frequency. We have a sampling rate of 48 kilohertz, and we only have a window length of 2048, so we should only be able to detect signal variations down to 23 hertz. So if I go back to a sine wave at 1 volt, again we get 0.707, so 1/√2. But now if I decrease the frequency, maybe to 10 hertz, you can see our RMS detector, or our moving recursive RMS, isn't doing very well. If I move it down to 5 hertz, it's not detecting that very well either. That's because our horizon isn't long enough. If we go to 50 hertz, we're getting closer to the actual RMS value. We have to go quite a bit above. So for example, 100 hertz is almost there at the actual RMS value. So keep that in mind when choosing L and choosing your window length. Thank you very much for watching this video. I hope it was useful, and I hope you can use the moving recursive RMS detector in one of your own projects. If you liked the video, please leave a like, a comment if you have any questions, and don't forget to subscribe to stay up to date with any latest videos. Thanks again, and I hope to see you in the next video. Bye bye.